In the name of Allah, in this lecture, I will discuss the most important basic concepts of the electrical power system, which are essential for studying and understanding capacitors and how to improve and correct the power factor. First, we must understand that the electrical power system consists of three main parts. 1. The electrical power source. 2. The electrical service devices or equipment. 3. The electrical loads. The main source of electrical energy, or the electrical power source, is the generators, or more generally, the generation stations or power stations. These stations supply or feed various electrical loads with electrical energy or voltage. However, the electrical loads refer to the various electrical equipment and devices that consume electrical energy, such as motors, heaters, lamps, and so on. As for the service devices, they are the various electrical equipment that receive electrical energy from the source or power stations and deliver it to the electrical loads. Examples include power transformers, distribution transformers, power cables, and distribution panels. In general, service devices refer to all electrical equipment located in substations and transmission lines, whether operating at extra high or high voltage, as well as the service devices in distribution networks operating at medium and low voltage. So the electrical power system in general consists of the following. First, power stations. Second, the transmission system, which includes two parts: overhead transmission lines or underground cables and substations. Third, low voltage and medium voltage distribution networks. Fourth, electrical loads. Since this course focuses on capacitors and power factor improvement, I will talk in more detail about electrical loads. As I mentioned earlier, electrical loads vary and each type operates using a different system, such as motors for motion, heaters for heating, and lamps for lighting. So we must understand that electrical loads differ in how they receive and consume electrical energy. This, of course, depends on the internal components and elements of each electrical load. In general, the basic components and elements of electrical loads are: first, resistance, R, measured in ohms. Second, inductive reactance, XL, measured in ohms. Third, capacitive reactance, XC, measured in ohms. Before discussing these three components in detail, we need to understand a very important concept. I mentioned earlier the main components of the electrical power system, but we must also understand that, in general, the electrical power system is based on electrical voltage and electrical current. The important question is, what is the main source of electrical voltage? And what is the main source of electrical current in the electrical power system? Power stations are the main source of the electrical voltage required for the electrical network. We all know that the main component of a power station is the synchronous generator, which provides both the voltage and the frequency, typically 50 Hz or 60 Hz. Therefore, power stations are the primary source of both electrical voltage and frequency. These voltages can be increased or decreased to suit different electrical loads by using power transformers located in substations and distribution transformers found in distribution networks. As for the electrical current, the main source of this current in the electrical network is the various electrical loads. Therefore, we must understand that if these loads increase, the current will also increase. Additionally, if all loads are switched off, the current will be zero and no current will flow through any part of the electrical network. So, to operate any electrical load, we must have a suitable electrical voltage. This means that if we have different electrical loads, as we can see in front of us, and all of them operate at a low voltage of 220 volts, then the voltage applied to the motor is the same as that applied to the heater or the lamp. Therefore, there is no difference in voltage as long as these loads operate at the same voltage level, for example, 220 volts. However, the difference will be in the system and the value of the electrical current. This means that if the rated power of a load increases, the electric current will also increase. But when it comes to the form of the current, we must understand that the presence of voltage and current at the load creates a phase angle between them. As I mentioned earlier, the basic elements of any electrical load are resistance, R, inductive reactance, XL, and capacitive reactance, XC. These elements are responsible for shaping the form of the current. So, while the voltage applied to a motor is the same as that applied to a heater or a lamp, the form of the current required by the motor is different from that required by the heater or lamp. As a result, the phase angle also differs. This difference is due to the variations in the internal components of each electrical load. Therefore, I will now explain in more detail the differences between these components or elements. I will start by talking about the first element or component of electrical loads, which is resistance, R. For example, if we have an electrical load that is purely resistive and an AC voltage source is connected to its terminals, where the resistance value is measured in ohms and electric current, measured in amperes, will flow through this resistor. Now we want to determine the value of this resistance, R, and understand the form or waveform of the electric current passing through it. Using the equation in front of us, or Ohm's law, we find that voltage equals current multiplied by resistance. Therefore, the value of the resistance in ohms is equal to the voltage in volts divided by the current in amperes. As we can see in the figure, the electric current is in the form of a sine wave and matches the voltage wave, which is also a sine wave. Therefore, the phase angle phi between the voltage and the current is equal to 0. So, we must understand that if the load is a pure resistance, then the current wave is a sine wave. The current wave has the same shape as the voltage wave. The current wave is in phase with the voltage wave. The most common examples of pure resistive loads are heaters and incandescent lamps. As for inductive reactance, pure inductive reactance refers to a coil or inductor with zero internal resistance. So, when an AC voltage source, measured in volts, is connected to the terminals of this coil, an AC current, measured in amperes, will flow through it. So, when an AC current passes through the coil, it produces a magnetic field resulting in the appearance of inductance, L. Since the current in the circuit is alternating, there is a frequency present. Therefore, the combination of inductance and frequency leads to the appearance of inductive reactance, XL. This inductive reactance resists the flow of electric current in the inductor or coil. We must understand that the value of the inductive reactance depends on the inductance, L, and the frequency of the source. So we can calculate the value of inductive reactance, XL, using the following equation. Inductive reactance, denoted as XL, equals 2 times pi times the frequency, F in hertz, times the inductance, L in henries. Since this inductive reactance is present in the circuit, we find that the voltage, V, is equal to the current, I, multiplied by the inductive reactance, XL. That is, voltage equals current multiplied by inductive reactance, XL, and therefore inductive reactance, XL, equals voltage divided by current. As mentioned earlier, inductive reactance is measured in ohms. So the presence of a coil or inductor in the electric circuit means the presence of inductive reactance, which resists the flow of electric current, or in other words, delays the current, or shifts the current wave by 90 degrees from the voltage wave. A pure inductive reactance causes the electric current to lag behind the voltage by a phase angle, phi, of 90 degrees. We must understand that the negative sign indicates that the current is lagging. The most important examples of electrical loads with inductive reactance are transformers, motors, generators, and reactors. As for capacitive reactance, XC, a pure capacitive reactance is a capacitor with zero internal resistance. So, when an AC voltage source is connected to the terminals of this capacitor, an AC current, measured in amperes, will flow through it. So, due to the presence of an AC voltage across the capacitor, an electric field is produced between its two terminals or plates, resulting in the appearance of capacitance, C. Since the voltage in the circuit is alternating, AC, this implies the presence of frequency. Therefore, the combination of capacitance, C, and frequency, F, leads to the appearance of capacitive reactance, XC. Capacitive reactance resists the flow of electric current. Now, it's important to understand that the value of capacitive reactance, represented as XC, depends on both the capacitance, C, and the frequency, F. We can calculate the capacitive reactance using the formula XC equals 1 divided by 2 times pi times the frequency, F in hertz, times the capacitance, C, in farads. Alternatively, we can also calculate it using the formula XC equals voltage divided by current. So XC equals V over I. And just like resistance and inductive reactance, capacitive reactance is measured in ohms. So the presence of a capacitor in the electric circuit results in the presence of capacitive reactance, which causes the current wave to shift and lead the voltage wave by 90 degrees. Therefore, pure capacitive reactance causes the electric current to lead the voltage by a phase angle phi of 90 degrees. We must understand that a positive sign indicates that the electric current is leading. One of the most important electrical loads that exhibit capacitive reactance is the capacitor, which is used to improve the power factor. Therefore, I will discuss these capacitors in more detail throughout this course. I talked about resistance, inductive reactance, and capacitive reactance, and we now understand that there is a phase angle phi between voltage and current. However, we must remember that voltage is considered the reference for current, meaning it is the current that either leads or lags behind the voltage. But first, let's ask an important question. 1. What is the practical reason that causes the electric current to lead in a capacitor, lag in a coil, and remain in phase in a resistor? 2. Is the phase angle phi always exactly 90 degrees in a coil and a capacitor and 0 degrees in a resistor, or can it have different values? 3. Electrical engineering studies rely heavily on the phase angle phi between voltage and current. But the important question is, what is the true practical meaning of the phase angle phi? For example, if electric current passes through a conductor that has an electric voltage, where exactly does the phase angle phi manifest in this conductor from a practical perspective? Also, is the phase angle phi the same in a 50 Hz system and a 60 Hz system, or is it different? I will explain all of this in detail in the next lecture. Thank you for your attention. See you in the next lecture.